Welcome to the university. In this video we will discuss Maxwell's set of equations for electromagnetism. Before anything else, please extend your appreciation and like this video, share our content, subscribe to our channel and hit the notification bell to get updated whenever we post new videos. Please help us reach many students who are eager to learn. We also have promos where you can win prizes. Check out the link in the description box below. As mentioned a while back, we will discuss Maxwell's equations for electromagnetism. As a matter of fact, Maxwell did not derive all of these equations by himself. Instead, he is the one who recognized its interrelatedness. We will start the discussion with Gauss' law of electric flux. This law relates the electric force present in a region that exerts a force on nearby charges, making the field a vector field called as electric field. The law states that the electric flux surrounded by a closed area is proportional to the magnitude of the charge enclosed therein, divided by the fundamental constant called as permittivity of free space. These flux are the only ones that are perpendicular to the surface. We derive the formula for Gauss' law. We start with the derivative for the electric flux. This is equal to E dot product A cosine theta. When we use the close integration, we will see that the total electric flux is equal to the electric flux E times the area A. This can be written in terms of the fundamental constant K, and we write it as 1 all over 4 pi E sub 0 times the quantity of Q over R squared times area A. We can simplify this and we will see that the electric flux is equal to the magnitude of the charge present in the closed surface divided by the fundamental constant called as permittivity of free space. Gauss also has his law for magnetism. You may think that there are also magnetic monopole just like a lone charge, but there is none to have been observed in nature. Gauss' law for electromagnetism states that the magnetic flux on a closed surface is equal to zero. We also know about the works of Michael Faraday, that is a changing magnetic flux produce a non-conservative and changing electric field in an empty space, an electromotive force and an induced current. The next equation that we are going to talk about is Ampere's law. This will help us calculate magnetic fields for highly symmetrical situations. A closed loop of any shape surrounding a current-carrying conductor is producing a magnetic field along this loop. If we want to know the total magnetic flux, we have to sum it up. That is, apply integration process in the path taken by the loop. We will see that the magnetic field is always proportional to the product of the current enclosed and another fundamental constant in nature called as the permeability of free space. This is also called Ampere's circuital law. We can now re-examine Ampere's law in the situation of the capacitor, and here is where Maxwell took advantage of mathematics and modified this concept. If we try to apply Ampere's law in a capacitor, we will notice that it will have a zero value at the space of the capacitor. We know that a capacitor accumulates charge. The amount of charge at the capacitor is calculated using the formula Q is equal to C times V. Capacitance C is equal to the permittivity of free space multiplied by the area of the capacitor plates divided by the distance of separation in between the plates. So we can simplify the formula in calculating the charge in the capacitor as Q is equal to the permittivity of free space multiplied by the area of the capacitor plates divided by the distance of separation in between the plates multiplied by the electric field E present in between the plates of the capacitor and the distance that separates them. If the charges in the capacitor is changing over time, we can say that there is a current present at the plates of the capacitor. This is called as the I sub C or conduction current. But if we draw a loop passing this bulging end of the capacitor and using Ampere's law, it implies that it can't be zero. As a matter of fact, Ampere's law can't have two values at the same time. Maxwell then invented a fictitious current called as displacement current. Displacement current I sub d is also equal to I sub c. Ampere's law can now be saved and can now be written as, with the conduction current equal to, and since I sub c is equal to I sub d, we can write Ampere's law in its complete form. These laws can be used to prove that light is an electromagnetic wave and it has a constant speed.